Welcome back. We're going to continue our discussion on Chapter 3, the arrangement and parts of the periodic table, as well as element groups. This corresponds to sections 3.4 through 3.5 of your textbook. So our modern periodic table is based on a periodic table developed by Dmitry Mendeleev in the late 1800s, in about 1869. Mendeleev noticed that when elements were arranged by increasing atomic mass, that elements with similar properties repeated at regular intervals or periods. This is kind of like repeating measures of music. If every 4 measures of music, a part of the melody repeats, this is kind of like what the periodic table does. Every 8 to 14 to 16 elements along the line, when they're lined up by increasing atomic mass, you get this repetition of properties related to that element. And so our modern periodic table is arranged by increasing atomic number. So the smallest atomic number is in the upper left, and it goes from left to right and then top to bottom. So hydrogen is located in the upper left corner. It has an atomic number of 1. And then you read across the table. So you skip a bunch of space in the middle, all the way over to helium, which is on the far right corner on the top, with an atomic number 2. And then you go down to the next row and you read it across. So hydrogen, atomic number 1, to helium, atomic number 2, down to the next row to lithium, atomic number 3. So you read left to right, top to bottom. And when we set up the periodic table this way, elements that have similar properties are grouped together in columns, which in chemistry we call those groups. So if you can understand periodic trends, you're going to be able to figure out a lot of chemistry in this class just based on the periodic table. And for me, this is one of those kind of epiphany moments in chemistry. I remember groaning a bit when we got to the part of the class in my Gen Chem class where we started talking about the periodic table, thinking that I was going to have to memorize the table. And to me, I'm not a memorization person. That was a really daunting task. But then when it was explained that it's based on these repeating patterns, if you can kind of get the pattern, you don't have to memorize it. You just have to apply the concepts kind of down and across the table. And so we're going to talk about some of those patterns and some of those repetitions or intervals that occur in the periodic table and why it's set up the way it's set up. So this is our periodic table. I'm going to post one on Canvas. In the rest of this class, you're going to want access to a periodic table. I suggest printing one off, and I'll post one on Canvas that's printable so that you always have one in front of you when you're taking quizzes and exams and can easily reference it. It's also a good idea in this section of the class to, if you're able to, maybe print off a couple extra copies so you can color code them and draw on them and label them to get extra practice learning how the periodic table is set up. Okay, so first thing, across the top of the table are columns. In each column we call a group. The columns are numbered from left to right, 1 through 18. So if you just go straight across numbering, grab my pen here, straight across numbering, you can see we start with 1, 2, 3, and so forth all the way across to 18. And this is what I would call the more current way that people refer to the periodic table, by just numbering straight across. And I think it's easier because you're not going to forget where something's located if you can just grab your periodic table and number it straight across. But a lot of periodic tables also number based on a Roman numeral and a letter. And so I put both ways on this slide. So here's just the straight across numbering way. And then below I put the Roman numeral and the letter. So the first column, you can call that column 1, or you can also call that column 1A or group 1A. The second column, you can call that group 2 or group 2A. The third column, you can call group 3 or group 3B. And you'll notice all the B Roman numerals are in this part of the periodic table that's kind of dropped down lower than the rest. This part down here. This is where all the B's are located. And these are what are called the transition metals, and we'll talk a little bit more about these later in this lecture. So there's the 2 ways of numbering the columns, straight across 1 through 18, or this A and B Roman numeral method, where all the columns that kind of stick up above the B's are part of the A numbering system. So it starts with 1A, 2A, and you do the B's, but then over here you start again with 3A. It's like the A's just kind of skip this B section. So you go 1A, 2A, skip the B's, and you go 3A, 4A, 5A, 6A, 7A, 8A. And those ones use the Roman numerals. The way that I can quickly, especially for the right-hand side of the periodic table, remember these two different methods is that if I always just number across 1 to 18, then the Roman numeral corresponds to the second letter and then the second digit in the number. So column 13 is 3A. Column 14, which has a 4, is 4A. Column 15, which has a 5, is 5A. Column 17, which has a 7, is 7A. So that's a way that I can remember both systems. It's a little trickier with the B's. Typically in the B groups, the Roman numeral way is more outdated and just the straight across numbering is used. So the columns we call groups, and then going down the periodic table, the rows we call periods. And so any elements that are in the same column or group tend to have similar properties. And so by just looking at the periodic table, you can look at something like neon over here in group 18 or 8A, and neon, helium, argon, krypton, xenon, radon, they all have similar properties because they're all in the same column of the periodic table. Isn't that cool, right? You already just learned something really major about the periodic table, that things that are in columns have similar properties. So any element on the periodic table can be specified by giving its group number and its period. It's kind of like playing Battleship. You might say, okay, I'm interested in sulfur. Well, sulfur is group 16. If you label across, it's in group 16, and it's the 1, 2, 3, third row down. So group 16, or 6A, period 3. And again, the rows we call periods, and the columns we call groups. So group 16, period 3. So any element on the periodic table, you can identify or specify just based on kind of its coordinates. And again, I like thinking of playing the game Battleship. I should actually come up with like a periodic table Battleship game. That'd be kind of cool. We also can specify elements based on if they're what we call main group elements or transition elements. So main group elements are all the elements on the periodic table that are in the columns that stick up above the B group. So if we check our groups, all of our groups that have the A Roman numeral that stick up above the rest, all of these ones, these are all part of what we call the main group, or sometimes called representative elements. And these elements all have properties that can be largely predicted simply based on their location on the periodic table. So anything that's in this area, right, any down all these columns, or in this area, any of these elements, we could predict a lot of what it's going to do, how it's going to react, if it's going to be a solid, liquid, or gas, etc., simply based on where it's at on the periodic table. And so we call those the main group elements. And this is why some people like the A-B numbering system, because every A column is a main group element. Okay, next. After the main group elements, we have what are called the transition elements. These are the elements that are in the B group or kind of dropped down on the periodic table. So all of these elements in here, these are all of our transition elements, or B group elements. And the elements in this part of the periodic table, it's not as easy to predict their properties just based on their position. You kind of have to individually, one by one, analyze them in order to know what their properties are. Unlike the main group elements, where if you had no idea what some of the properties of bromine are, if you knew some of the properties of fluorine, you could guess what many of the properties of bromine also are, because it's the main group element. But in the middle of the periodic table and the transition elements, the properties aren't as predictable. Next, we have this dividing line, the staircase, and this shows the division between the metals and the non-metals on the periodic table. So you start up here next to bromine, to the left of bromine, and you just make a staircase. Just getting ahead of myself. You just make a staircase going down and to the right. And that staircase shows you the division between the metals and the non-metals. So everything to the left of the staircase are metals. And so the whole lower left and center of the periodic table are metals. Metals tend to be good conductors. They conduct electricity. They have luster, which means they're shiny. They're malleable, which means many of them are bendable. They're ductile, which means many of them you can stretch into wires. And they tend to do what's called lose electrons. So if an element loses electrons, it's losing negative charge. So metals tend to form cations. When they're going to make an ion, they tend to lose their electrons, and they tend to make cations because when they lose an electron, they end up with more protons than electrons. And all of the metals are solids at room temperature except for mercury. On the other side of the dividing line between the metals and the non-metals are the non-metals. So these are on the upper right side. They have varied properties, but they're usually poor conductors. They tend to not have any luster, so they're not very shiny. And unlike the metals that tend to lose electrons and make cations, the metals tend to gain electrons to make anions. So remember, an element in its elemental state has an equal number of protons and electrons. So if nonmetals tend to gain electrons, they're gaining negative charge, which means they tend to make negatively charged ions, which are called anions. And there's 23 elements classified as nonmetals. So most of the elements on the periodic table are classified as metals. We have 118 elements, and only 23 are classified as nonmetals. So some familiar metals, we have aluminum, lead, tin, and zinc. And you can see they've got that luster. Many of them you can bend or flex, they're malleable, and many of the metals can be stretched into wires like copper wires. And on the right, we have nonmetals. So some you might be familiar with are sulfur, that's that yellow powder, phosphorus, which is the dark red powder, and then bromine, which is that reddish brown liquid. So the elements that are right along that staircase, and I circled them in pink here, and on this color-coded periodic table, they're kind of a light sky blue color. These are called metalloids. And they're pretty much just along the steps of that dividing line between the metals and nonmetals. They include bromine. You can circle them as we go. So they include bromine right here. Sorry, trying to find a really good way to highlight these. So they include bromine, silicon, germanium, arsenic, antimony, terbilium, and polonium. So these are the metalloids. And like I said, they're pretty much along the dividing line. Aluminum is a metal, even though it's along the dividing line, it's classified as a metal because it has the properties strictly of metals, where it's a good conductor and it's malleable and it's shiny. Versus the metalloids, they tend to be a little of each. They have properties of both metals and nonmetals. And so metalloids are really cool because they're oftentimes semiconductors. Remember, metals are good conductors generally. They conduct electricity well. And nonmetals tend to be poor conductors. They don't conduct electricity well. So these metalloids, you might recognize like silicon from computer chips. These metalloids can conduct or not conduct depending on their surroundings and their properties. And so we can kind of, with these metalloids, essentially turn them on and off to conducting electricity. And so that's why they're used in semiconductors and a lot of electronics, where we want the ability to turn on or off the flow of electrons to send a signal or stop a signal. Okay, we're going to go through now and name some of the groups. So we talked about the main group elements. Those are all the columns that stick up from the rest of the periodic table. We talked about the transition elements. It's the part that lays lower than the rest of the periodic table. We talked about the staircase between the metals and the nonmetals. We talked about properties of metals, properties of nonmetals, and then that along that staircase, there are the metalloids, which have properties of both metals and nonmetals. It's useful to be able to name specific groups in the periodic table because they're very important chemically, and they're ones we're going to be referring to a lot throughout the class. So the first one all the way over on the left is called the alkali metals, and we call this group 1 or group 1A. And so they're all the elements in group 1 excluding hydrogen. They're all soft, shiny metals, and they react readily with water. So if you want to see something really cool on YouTube, search for sodium exploding, potassium exploding, rubidium exploding, any of these elements in the first column. Because they react readily with water, if you take a piece of sodium or potassium or rubidium and toss it into water, you get a violent reaction, which usually results in an explosion. So there's these videos on YouTube where people take lithium, it's a small reaction, and then they take sodium, it's a little bit bigger, potassium's even bigger, and then rubidium, you get a huge explosion. And in actually some of the labs, we sometimes work with sodium, unfortunately not in 305. But if you keep taking chemistry, you'll get to work with sodium where you drop it in a test tube with water, there's a small explosion, and then you can light the gas that's given off on fire to get another explosion. It's pretty cool. So those are the alkali metals, group 1 or 1A. Right next door to them are the alkaline earth metals. They're group 2 or 2A. They're also soft and shiny metals, but they don't react as vigorously with water as the group 1A metals. So they react moderately with water. Skipping across the table all the way to group 17 or 7A, these are called the halogens. They tend to be gases at room temperature or slightly above, and they're highly reactive. And then next to the halogens, the column that's all the way on the right-hand side of the table, group 18 or 8A, these are called the noble gases. They're all gases. They're not very reactive at all, and they undergo few chemical changes. So we've got the alkali metals, the alkaline earth metals, the halogens, and the noble gases. And then we have this part of the periodic table that kind of looks like it was cut out and taped or pasted below. And that's a great description because that's actually kind of what happened. To make the periodic table more compact, a placeholder was put in the periodic table for what we call the lanthanide and the actinide series of elements. So these elements should be, where I circled here in black, they should be here in black, where these black space holders are, stretching out 14 spaces across to make a really long periodic table. But that would be really difficult to display compactly. And so what chemists did is they put in two placeholders here, with lanthanum being the first, where the first placeholder is, and actinium being where the second placeholder is, hence their names, the lanthanide series and the actinide series. And we just kind of cut those out and put them down below, and then squeeze the rest of the table together. And so what it would look like if we didn't do that is this top periodic table. If lanthanide and actinide, the lanthanide and actinide series, were in the table where they're supposed to be according to their atomic numbers, it'd go from atomic number 55, 56, 57, and then lanthanide is atomic number 58, it'd be here and stretching across, and actinide is 90 and stretching across, and it would elongate the whole table. So instead of doing that, we just cut this portion out and we display it below the periodic table. And then the rest of it we squeeze back together. So you can see it goes from 57 to 72 when you're reading across on the periodic table, because you have to recognize that there's a placeholder here on the periodic table where these elements are supposed to go. Okay, so we're at the end of talking about the periodic table for now. We're going to, in the next part of chapter 3, talk about electrons and how they define the chemical properties of an element and how we in detail discuss the location, the energy, the orbitals that electrons are in. And that's another component of how the periodic table is arranged. So we'll come back to the periodic table again at the end of chapter 3 to talk about how the periodic table is arranged not only by physical properties like we talked about here, like different types of metals, what they react with, if they're gases or solids, if they conduct electricity or not, but also that the periodic table is arranged based on the electrons in atoms. And so before we do that, you should take a minute here to summarize what you've learned so far in chapter 3 before we shift gears to talking about electrons. So summarize what you think the 3 most important topics or concepts are from today's lecture by writing those concepts in 3 sentences in your own words. And that's a really good way to wrap up and summarize what you've learned so far. And it can be a way to also help you identify any areas that you want to go back and continue to review. So we'll pick up next lecture with talking about electrons, and the whole second half of chapter 3 is about electron configurations, how they're organized around atoms and orbitals, and then how the periodic table also shows us information about the electrons based on the shape and the organization of the periodic table. All right, I'll see you then. Thanks.